Okay, this is Physics 1A for March 29th. Today we're talking about work and energy, and it's a lot of stuff to talk about, but we'll do our best to get through all of this. All right, so what is work? The meaning of the word work in physics is a little bit different than the meaning of the word work in kind of the rest of the world. When we say work in just common parlance, what we mean is like your job or homework or something like that. Work may involve, let's say if you're a construction worker, it may involve lifting things, building things, running machines, shoveling things, whatever. That's what we mean by work, doing things that, where we exert some type of our physical effort to do things. In physics, it means something very specific. In physics, the word work is something that you get when you combine a force and a distance. So it's basically something that happens when a force is applied over a distance. Okay? And first thing we're going to talk about is the work done by a constant force. So when you have a constant force, for example, if I have, this will be the first example that we look at, is if you have like a box and it's resting on a flat surface and you pull it with some force, and that force is a vector, and let's say that you take this object and you move it over to some position like right here across like a relatively flat surface, and the distance that you move it in this direction, let's say that you call that distance like d, then, well, let's make it a vector. Let's say that the displacement the object moves through in the x direction we call delta x, like this. Then the work that's done is going to depend on the force, the distance, and the angle between the two of them. So if we define this angle right here to be theta, then we can define work to be equal to the force, magnitude, multiplied by the distance, magnitude, and then multiplied by the cosine of the angle between the two of them. Why do we multiply by that cosine? The reason why is because this force F can be broken up into components, where one component points this way, and that component is going to be F times the cosine of theta, and another component is going to point upwards. The component that points up doesn't do any work at all. It's really only this force right here, this component, that actually drives the object forward. So we say that's the thing that's going to be doing the work, and the F cos theta shows up in this equation right here. So this is our kind of simplest definition of work, but we can also use something that we learned about in the first chapter, which is called the dot product, to write this in a slightly more general way, which is if we take the dot product between the force and the displacement vector, then we get the work that's done. So this is the work done by a constant force. Okay, and we're going to do a really simple example of this. So let's say that we take a flat surface like this, and on that surface we put a box. Make it a different color. And let's say that this box is pulled by a force similar to the one that I did here, but let's actually use like a vector symbol for it. So we have a force that goes up like this, and let's say that the value of that force is equal to 200 newtons. And then this object is going to have a mass as well. So let's say that the mass of this object here, m, is equal to 10 kilograms. And let's say that we apply this force on our object until it moves through a distance of, let's say like 5 meters. So let's say it moves from here to here. So it moves over a distance, which we'll also use a vector for. So it goes from here to here. And let's say that displacement, we call it delta x. And let's say that it's 5 meters. So up here we'll just write that delta x is 5 meters. In addition, let's also add work into this problem, or sorry, friction into this problem. So let's say that this surface down here has a coefficient of friction, u sub k, that's equal to 0.2. And I'm going to write this up here. So we're going to need to draw on this picture. So what I want to do is I want to calculate the work done by all forces acting on the box. By using our definition right here of what the work done by a constant force is. Okay, so let's go through and do the, I guess, so-called easy part first. We want to label all the forces that are acting on this box here. So what we're going to have is there's going to be a normal force acting on the box from down here. There's going to be a weight pulling down on the box. And there's going to be a friction force. Going back this way. And so we want to find the work done by all these forces, and I realized there's something else I left out, which is we are also going to need the angle right here. So this angle, let's say, is equal to, I was going to do 60 degrees. We can do 60 degrees. I would just need to move this up a lot. We'll just do that and say the angle here is 60 degrees. All right, so we want to find the work done by all forces. Let's start with the force F. The work done by the force F is going to be equal to the size of the force, which is 200 newtons, multiplied by the displacement. So the object moves from here to here, so the displacement is 5 meters. And then we multiply by the cosine of the angle between the two of them, which is 60 degrees. So I think this is going to give us something like 500. And the units for work are going to be newtons times meters. So let's see what that is. So 1 newton times a meter, or 1 newton meter, is equal to, what is this equal to? Certainly some of you know. What's the unit that we use for work? The joule, that's right. So this is equal to 1 joule, capital J. That's the unit that we use for both work and energy. All right, so the work done by the force F in this case would be 500 joules. Anyone have any questions about that? All right, let's do the work done by the normal force next. So the normal force, we would need to know what the value of the normal force is before we can really do this. So in order to figure out the value of the normal force, what can we do? Yep, sum of the forces in the y direction has to be equal to 0. So if we do that over here, we say the sum of the forces acting on this object in the y direction is equal to 0. We're going to have N minus mg, and then plus, I would say this force F is going to have a component that's going to be F times the sine of 60. And I'll draw that on the picture too. So we'd have to have components for this force F, and one of them would point like this. And that force would be the kind of y component, and that would be F times the sine of 60 degrees. So we get this equation right here, which allows us to solve for what the normal force is. So the normal force is going to be equal to mg minus F sine 60. Okay, so that's equal to a number, right? Now, I don't know what it is. It's equal to a number, but I'm just going to show you that it's not really going to matter. Oh, well, we actually are going to need to know it. So let's calculate it. So the normal force then is going to be equal to, the mass was 10 kilograms multiplied by gravity, and then minus F, which is 200 newtons, multiplied by the sine of 60. Okay, could you all calculate this for me? I'll do the same.
Negative 75.2.
Oh, did I not make this thing heavy enough? This is what happens sometimes when you just pick numbers. Okay, so that means that the upward force on this object is bigger than the weight, right? Alright, we're going to have to make the weight bigger here. How much bigger are we going to need to make it? Is 20 enough? Yeah, 20 would be enough, right? Alright, I apologize. It means it's being lifted off the ground, Andrew, I believe. Wait. Shouldn't that be what it means? If n is negative? I don't know what that means. It doesn't mean. It actually doesn't mean anything. I think it means that it's pretty simply what it means is that this force down over here is bigger than the weight. That's all that means. It means the force here is bigger than the weight. So if we change the mass to 20 kilograms, that should work, right? I think that should be fine. So let's go in here. Let's change this mass right here to 20 kilograms. Does that work? That should work. This is all because I changed the angle to 60 degrees. If I'd made the angle like 30 degrees, it would have been fine, but I just wanted this number to be half. Anyway, so you get 22.8. So that's our normal force. It's going to be 22.8 newtons. Okay, coming back to find the work done by that force then. Let's kind of shift this stuff over and make it a little bit smaller. All right, to find the work done by that force then, we just take the size of the force, 22.8, and we multiply by the distance that the object moves, or the displacement, which is 5 meters. And now I need to multiply by the angle between the displacement vector and the normal vector. What's that angle going to be? Yep. And cosine 90 is 0, so the answer is 0. So the work done by the normal force is 0 joules. Okay, what about the work done by the force of gravity? Work done by the force of gravity should be equal to 20 times... So the weight of this object should be about 196 newtons, I think. 20 times 9.8. Again, you multiply by 5 meters, and then we multiply by the cosine of the angle between the weight vector, which is down, and the displacement vector, which is to the right. So again, you get cosine 90, which is 0, so you get 0 joules. So both the normal force and the weight in this particular problem are not doing any work. It doesn't mean they won't do work in other problems, although I will say in general, the normal force pretty much never does work because it is almost always perpendicular to the path that something's moving along. Now, it could do work, for example, if you're lifting an object. That would be an example, but anyway. Often it'll be 0. Any vertical force will have work 0. Yep, as long as it's moving along a flat surface. If it's moving along an angled surface, it won't be true anymore, Summer. Because then weight will do some work, right? But the normal force won't. I suppose we could do a quick example of that after this if you want to. Alright, so the weight done by the weight is 0. Sorry, the work done by the weight is 0. And the final, we want to do the work done by the friction force. So this is going to be equal to the size of the friction force multiplied by 5 meters. And then multiplied by the cosine of the angle between the friction force, which points left, and the displacement, which points right. I said 196 is equal to 20 kilograms multiplied by 9.8. That's what that is. It's the weight. So friction force, what's the angle between the friction force and the displacement vector? Displacement vector goes to the right, the friction force points to the left. What's the angle between those two? 180 degrees, that's right. And cosine 180 is equal to -1, right? Now we also need to plug the friction force in here, and friction force is going to be equal to mu k, which is, I said, was equal to 0.2 in this problem, multiplied by the normal force, which we calculated here. And then cosine 180 is -1. And so if you multiply all that together, we're going to get, well, 5 times 0.2 is 1, so Because 0.2 is 1/5. So this is going to be equal to negative 22.8 joules. That's equal to the work done by the friction force. The friction force will almost always do negative work. And this kind of shows us something about work that we're going to talk about here right after this, which is that work can either be 0, it can be positive, or it can be negative, and work is a scalar. So the units are joules, it's a scalar, it can be 0, it can be positive, it can be negative. Work done by friction is almost always going to be negative, because friction tends to oppose motion, right? Now to answer the question that you asked, Summer, suppose that instead of moving along a flat surface, instead we had an object that was sliding up a ramp. So let's say that I have a block that's here, and let's say it's being pulled up the ramp. Maybe just to keep things simple, let's say that we pull with a force that's parallel to the ramp in this direction, and we move the box by some distance here, from here to here, that we call delta x. You can't see the side? Oh, no. Oh, was this thing blocking right here? Is it okay now? Sorry about that. All right. Okay, so suppose something's moving up a ramp like this, and we want to label the forces that are acting on it. Well, you're going to have your normal force acting up this way. Let's make all the forces red. You're going to have your weight pointing down like this. You might have some kind of a friction force pointing along the ramp like back this way. And then you'd, of course, have the force itself that's pulling up the ramp this way. Right, so you're going to have normal force, you'll have friction again, and now you'll have the weight pointing down like this. But now the weight actually will do work. Okay? What's the angle between the force vector and the displacement here? 0. What about the friction force and the displacement? 180. And then what about the weight and the displacement? So we don't have enough information to immediately answer that. So what we need to know is what was usually given in a problem would be like the angle of the incline down here. Right? So if that angle is theta, what we can do is we can kind of draw a perpendicular line like this and say that this angle is theta right here, okay? And so how about now? If I tell you that this angle is theta, if I wanted to write the work done by the weight, I would write the force is the weight, I would multiply by the displacement, and then I would have to multiply by the cosine of the angle between those two. What would it be equal to in this case? Yep, 90 plus theta, that's exactly right. It'd be 90 plus theta, because it's 90 degrees there, plus the theta, and it's that whole angle that is the angle between the displacement and the weight. Now let me ask you this before you actually calculate this. Is this going to be positive or negative? Negative, yeah. And hopefully that makes sense, because the idea is that you need to put effort in terms of a force, right? You have to pull to make an object like this move up a ramp. So gravity is going to be working against you. So that's what negative work really is. It just means that that force is, well, it's working against you. It's the opposite of working for you. Like something working for you is positive, something working against you is negative, right? To distinguish between those things, we can look at a really, really simple example. So let's consider someone that is that's lifting weights, okay? And let's say that this person is going to lift a barbell from this position here. So they're holding a barbell in their hands right here. So they're grabbing onto this here. They're holding it in this position. And what they're going to do, this person's going to do, is they're going to lift the barbell in this direction, okay? So the question I would ask is the work being done by the person when he lifts the object positive or negative? Positive, right? Why is that? Because the displacement is up, call that delta y or something like that. And the force is also up, right? If they point in the same direction, the work is positive, okay? What about the work done by gravity? It's negative. So you see what I mean? That you're kind of doing work. When we say you're doing work, in the physics sense of it, you're always, almost always, doing work against something else, right? In this case, you're doing work against gravity, right? And if your goal was to like lift weights to, build muscles, you have to do work against something, right? You can't build muscles by exerting effort against nothing, right? So if there was no gravity, for example, if this person were to do this same lift, but they were on like a space station that didn't have any gravity at all or very little gravity, then they wouldn't be doing any work and it wouldn't help their muscles get stronger. So you kind of need that thing to be doing work against if you want to actually do any work or build muscle or something like that, right? That's why any type of like weight machine that you use is going to have something that you're doing work against. Like if you're doing bench presses on like a kind of standard like weight machine, you're going to be lifting actual mass. You're going to be pushing mass upwards, right? Like in this case here, there's something that has weight and you lift it upwards, right? But you can also have similar things where the resistive force is coming from like a rubber band, or it can be coming from a magnet or whatever. But in general, when we say you do work, you're doing work against something, okay? And in this case, the work you do is positive, but the work done by gravity is negative. So what if we look at the other piece of this cycle? So what if we look at the situation where the person has already lifted the weight, so the weight is like up here. So they're holding this barbell up here. And now what they're going to do is they're going to move it downwards. So this is going to be our delta y now. Okay. So the person lowers the weight. So what about now? What's the work done by the lifter going to be? So we have to think about the direction of the force the person's putting on this. So this person, when he lowers the weight, or she lowers the weight, what direction is the force that the person places on the barbell? Is it down or up? So you're saying that the force that the person places on the barbell is downwards when they pull down like this? It's up, right? This person exerts a force here and exerts a force here, because if they didn't, the object would fall down to the ground, basically, right? So this is the force of the person. Both of these are. And the weight goes down, right? The weight of the barbell points down like this. So let's start with gravity. If the weight points down and the displacement also is down, so you're taking this thing and you're lowering it, right? You're lowering the object downwards. So the weight is down and the displacement is down. Is the work by gravity positive or negative then? Yep. And because the force of the person points up and the displacement goes down, they're at 180 degrees away from each other, which means the work done by the lifter then has to be negative. Now, just because we say that it's negative work doesn't mean that lowering the weight doesn't also increase your muscles, right? Because this isn't easy to do. So don't confuse positive and negative work with being like, I don't know. It's not like one of them takes effort and one doesn't. It's that they both take effort, just kind of in different ways. Between these two things, probably lifting the object is harder than lowering the object. Because if you want to lower the weight, you could of course just let go of it and gravity will naturally bring it to the ground, right? But if you want to lower the weight so that you can repeat this process over and over again, then you're going to have to be careful about the way you lower it. And being careful about it means you need to exert an upward force so that the weight doesn't just like drop to the ground. And, you know, each one of these things will help to build your muscles as you repeat doing these things, right? All right, so you have any questions? Positive, negative work? To get 0 work, the person would just hold the weight still, okay? So if this person just held the weight in either one of these two positions but didn't move it, that would be 0 work. But again, just because it's 0 work doesn't mean that it also is easy, because in order to hold a really heavy weight, when you would be lowering the weight, would it be positive or negative weight? What do you mean negative? I mean, weight is just... I mean, weight is pointing downwards. Oh, negative work. Okay. When you would be lowering the weight, would it be positive or negative work? Negative. It's negative because the person's force is up, but the displacement is down. Anyway, so to go to the other situation, if the person just holds the weight, so if you take an object and you just hold it up with your hands, according to physics, this doesn't actually take work. Okay? It doesn't take any work at all. And again, to compare to what we think of as effort, because I think work and effort are things that can kind of get confused. It does take effort to hold this object up, right? If I take like a 50-pound bag of dog food, for example, and I try to hold it in my arms, and I just try to hold it there for a long period of time, my arms will eventually get tired, right? Would everybody agree with that? If you take any heavy object and you try to hold it in your hands at a fixed position for a long period of time, your arms are eventually going to get tired, right? Does everyone agree with that statement? But according to physics, you're doing no work at all, okay? That doesn't take work, according to physics. In reality, you know, there's things happening inside of your joints, like I don't know enough about biology to say exactly what's happening, but, you know, there's tension within your muscles when you do that. And that type of tension really takes effort for you to sustain, so... it doesn't mean that it would be easy to just hold a really heavy object for a long period of time. It just means that according to physics, there's no work being done. Okay. Now there could be chemical reactions that are occurring in your body that require energy, and over time, yeah, that can wear you out. But that's a different story. Okay. So that's the work done by a constant force. Okay. And I'm just curious. Probably everyone in here has seen this relationship before, is that right? Like in your 2A course, you saw work equal to force times distance times cosine of an angle? You all saw that in your... Okay. So what's new in Physics 1A then is looking at the work done by a variable force. So let's talk about that. It's a little trickier. Okay, so for the work done by a variable force, what we do is we say that we can break up the motion of the object into kind of small different pieces, and we can use that as a way to describe the way that this work is being done. So to define this, let's start off with a coordinate system. And let's say that on this coordinate system, what we're going to do is we're going to plot a force that's applied up here on the y-axis as a function of x. So this is going to be a one-dimensional force. And what I'm going to do is I'm going to say that this force is going to vary over the distance that we're pushing it, okay? And to get a picture associated with this so that it's kind of maybe clear what we're doing here, let's say that what we're doing is we are taking a box and we're pulling it with a force F, but that this force F is a function of x, okay? Meaning that the force is going to change as we move it along this displacement right here. Starting from x equal to 0 at this location, moving over to x equal to whatever at this point right here. And as we pull it, which is probably normal for the way people actually pull things, sometimes we're going to pull hard and sometimes we're going to pull weakly. So we're going to change the force that we pull with as we move. At first, maybe we pull at 50 newtons, and then maybe our force gets a little weaker to 30 newtons, and then 20, and I don't know, back up to 50. So basically, we're pulling this, but we're just not pulling it with a constant force. Hopefully that idea makes sense. Just imagine you're pulling like a kid in a wagon or something like that, and you know you're pulling them along, and then you stop sometimes, and you pull them a little bit more. And let's say that when we're doing this, that we can actually describe what our force looks like by saying that it kind of like gradually increases, maybe it rapidly increases, then maybe it kind of like just goes off like this. But we have a function that defines the force as a function of displacement, basically, right? All right. So what we want to do is, in order to understand how we could calculate the work that's done by this force, we basically want to break up our displacement into a bunch of little tiny chunks down here. Okay, so we'll say that we move a little bit, and then we move another little bit, and we move another little bit, and so on and so forth. So we break our displacement up into a bunch of little chunks right here. And then for each chunk that we break it up into, we basically are going to drop a line. Let's see if I can get a straight line in here. We drop a line to represent, well, to kind of draw up to the curve. Like this. So now all we're really doing is just like drawing a line up to this curve right here. And we're breaking up our displacement into little tiny bits. I think that one's kind of tilted, but that's okay. All right, how many more of these do I actually need to draw? I don't know. Boy. Getting these to be straight by eyeball is kind of hard. I think I need maybe new glasses. Yeah, that's definitely what we're gonna do, Summer, that's right. Okay, so suppose that we just break it up into a bunch of little displacements like this. And we'll call that good. Okay. Now, of course, in order to use this, we're also gonna need to basically figure out what the value of the force is at each one of these points. So to do that, I'm just gonna kind of draw a little box where every one of these are. So these are all gonna be little rectangles here. And we're going to be able to define exactly what the value of the force is in each one of these cases, because what we'll do is we'll basically say, here, let's use this one as an example. If I come over here and look at the place where that meets this axis right here, that's going to be the value of the force at that point. So here's what we're going to do. We're going to label these. The first displacement down here, I'm just going to call delta x1. The second displacement, I'm going to call delta x2. And then delta x3, and so on and so forth. That's going to be the displacement between this point and this point right here. And then I'll call the forces the same. So the force associated with delta x1 right here, we're going to call f sub 1. The force associated with the second displacement, we'll call f sub 2, and so on and so forth. So basically, the force in the first rectangle is f1, second one's f2, f3, f4, f5, etc. And then we can just say that the work done during the first displacement would just be equal to F1 multiplied by delta x1. And we don't have an angle because we're saying basically that our force basically only acts in the x direction. You may even say that this is the x component of the force if you really want to. But that's going to add a lot of extra subscripts that I'm not going to worry about, that I don't want to worry about. So we're basically saying this force only acts in the x direction, or we could say this is just the x component of that force. That would be the work done along the first displacement. Does that statement make sense to everyone? Okay. You know, the force may be like, let's say 10 newtons, delta x1 may be 1 meter, so the work done here would be 10 joules or something like that, right? Now, if I want to find the work done over the whole duration, though, the net work done, or the total work, would be equal to basically F1 times delta x1 plus F2 times delta x2 plus dot, dot, dot. And we could simplify that in terms of a summation as the sum of F sub I delta xi. And then, I think Andrew mentioned, looks like we're taking the limit. That's exactly what we're going to do next. The next thing we want to do is, if I really want to actually know exactly what the work done here is, then what I need to do is I need to make the displacements that I made down here smaller. I really need to make them a lot smaller. I need to basically let the limit as the displacement goes to 0. But before we do that, I just want to mention that when I calculate the work done here and do F1 times delta x1, this basically ends up being the area of a rectangle, right? In fact, let's just make this all red. Or we'll just do it like this. This is the area of a rectangle. And the rectangle that it is basically this one right here, right? And then F2 delta x2 would be the area of the next rectangle, right? And so on and so forth. So keeping that in mind, what we want to do next is basically say that when we calculate the work done, or the net work, what we're going to really want to do is take the limit as delta x sub I goes to 0 of this summation. And when we take that limit, what this is going to give us is basically an exact representation of the area under the curve. Basically the area between the curve and the x-axis here. So like if we dropped a line right here, it would be, I'm gonna highlight it. It would be basically this area here. Right, that's what we would be doing, is finding all of that area right there. I'll get rid of all these lines because I think they make it look ugly, but that's the idea. The area under the curve, it means finding the area contained within this little curved piece and this down here. Now we don't really have exact ways to find the area of things that are curvy like this, but we do know how to find the area under the curve if we know what the function is. Because in calculus we learned that this whole thing right here basically turns into an integral of f dx from whatever your initial position is here to whatever your final position is. And that is going to be equal to the work done. As long as it's a one-dimensional force. Now, we can generalize this. Oops. To motion in more than one dimension. As the work done is now going to be equal to the integral. So we could basically do this in three different dimensions. We could write an integral for the x direction, the y direction, and the z direction. And this is what it would look like. Does that make sense? Keep in mind, I didn't include it on this problem here, but really this was the x component of the force that I was dealing with here. So I could get this relationship, mostly because I didn't want to have to worry about the fact that there could be some angle right here at the beginning, but we can actually add in the fact that there would be an angle if we wanted to. So this is what we would get. All right, the integral applies to everything here, in case that's unclear. It's the integral of all of this stuff summed. But there's a neater way to write this right here. So if I tell you that I can define a change of position vector or a displacement vector, I think we did this early on in class like this. dx I hat plus dy j hat plus dz k hat. Then I can write all of this in a simpler way. Let's scroll down. I can write it as the work is equal to the integral of the force. And we have to take the dot product now with dr. And this is the work done by a variable force. This is our most general definition. We call this a line integral. And if you've taken Calculus 1, you may not have seen this. Calculus 2, you might not have seen it. If you've taken Calculus 3, you probably have seen this idea. But I want you to understand that this is the same thing. Both of these statements are exactly the same. Okay? This f dot dr simplifies down to three different integrals, basically. 1 over x, y, and z. And really, we're never going to do integrals over z, so at maximum, it'll be over x and y. I write it like this because it's conceivable that you could have a problem where you don't want to write things in terms of x and y's. You may want to write them in like polar coordinates or cylindrical coordinates. And in those cases, this dot product integral is going to be more general. Okay. I'm going to give you two examples of how we can apply this. The first example, we're just going to use this definition here. Okay. So this is for a one-dimensional force. All right. So we need, if I want to use this definition of work as an example, then I need a force that really only acts in one dimension. Okay. And gravity is certainly a good example of this. Gravity really only acts downwards, right? That's a force that acts really only in one dimension. But gravity doesn't really change as long as you're close enough to the surface of the Earth. It does change as you start to get farther and farther and farther up, but gravity is not really a good example. What is a good example of something we can use that we haven't learned about yet, but you've probably heard of before, is the spring force. So let's talk about the spring force, and let's use it as an example of how we can apply this equation right here. Okay. All right. So how does the spring force work? So the idea for this is basically you need a surface, although it could be hanging, I guess, but it doesn't have to be. We need like a box, as we often do in physics. I can see that this isn't straight now. Whoa, I didn't mean to do that. I pushed F1. Okay, so there's our surface. Here's our box. Let's make it smaller. The string force, Math 191. Did you talk about you mean spring force? Okay, so the way I'm going to draw this, which is commonly the way these things are drawn in physics, is I'm just going to draw a little thing like this to represent my spring. But when I say spring, hopefully you understand what I mean. I basically just mean an object that can be compressed and stretched. They tend to look kind of more like this, although it's not like that's any better than what I just drew here, right? So I'm just going to draw this little jagged representation. This is my spring. It is attached physically to a box here. This box is going to have a mass m, all right? And the way the spring is going to work is it's going to have what we call an equilibrium position that we refer to as x equal to 0. This is the equilibrium position. The spring is neither stretched nor compressed. So the spring is just sitting there, it's balanced, it's not exerting any forces at all at this position here. But what we'll do is we'll just draw a second picture underneath it and talk about what happens when we do stretch it. So now if we take our box and we stretch it by moving it to some position here, okay, and I'll draw that by making the spring look a little bit more stretched. So now our spring is going to kind of be like a little more stretched out. Okay. Then what happens is that there's a force that gets exerted on this box that's dependent upon exactly how far you move in this direction here. So let's draw a little vector here. So if we displace this object in this direction here, so that this is a position that we call x right here, then there's going to be a force acting on the box, and the force is going to basically point back in the direction towards equilibrium. The force will always point back to the 0 point, like this. And that's going to be what we call the spring force, F sub s. It's a vector. All right. So the idea here is that we've pulled it out to here, and by pulling it to this position, there's going to be a spring force that points back in this direction here. The other possibility would be that we take the exact same system, and I'm still going to line that up, and instead of stretching it, the spring also works under compression. So instead of stretching it, if the box were to be pushed inwards, this like to here, let's say for example, so that the spring is now really bunched up, so this is going to be stretched string, this is going to be compressed string. So our spring has now been squeezed together. Then now the force is going to point to the right. The force always points toward equilibrium. Equilibrium is the center. So now the force is going to point to the right, like this. So that's our spring force now, F sub S. And again, it's going to depend upon the x-coordinate right here. And in this case, your x-coordinate is going to be negative, right? I don't know. X is equal to something. How can I write this? I'll just write x is less than 0 or something like that. But what we care about the x-coordinate of this object here, and we define that distance to be x. So over here, x is greater than 0. So what you notice when you look at this is that when x is positive, so if I define this to be the positive x direction, right, and I define this to be the negative x direction, and the middle is 0, right, this is x equals 0. When x is positive, is the force positive or negative? Negative. And when x is negative, is the force positive or negative? Positive, right? Okay, so there's clearly a relationship where the force is somehow related to the negative of the x component. Or x, not x component. Just force is related to negative something times x. Now, force is measured in newtons, right? And x is measured in meters. So we need something in here. And normally what we do is we just put a proportionality constant, k. And this is the spring force, where the proportionality constant k, well, it has units of newtons per meter, first of all, because you got to do meters times newtons per meter to get newtons, right? But yeah, that's your spring force. This is the kind of spring force that we're going to use in this class. It is a simple spring that obeys what we call, this is called Hooke's law. And the springs that we'll use in this class are just going to obey Hooke's law. Do all springs obey it? Probably not. Do they obey it over all displacements? Probably not. This is probably only true for certain springs for small displacements, x. So x you can't really stretch it too far, or else you may overstretch the spring. If you've ever taken like an old slinky or something like that, after you use it for a long period of time, the slinky doesn't work as well anymore because some of the like little pieces of it become a little too stretched, right? Okay, so the idea here is that this is going to work for small displacements, and the term k is what we call the spring constant. The larger that it is, the stiffer the spring is. So I think about springs on like trampolines. Trampolines have all these springs that are holding the trampoline together around the edges. Those would have a really, really, really high spring constant. Whereas the spring inside of like a toy pop gun or something like that may have a smaller spring constant. But this is a number that's usually going to be given to you in a problem, or else you'll have to calculate it in some way, right? So just as an example, let's say that I have a spring that has a spring constant that's equal to 100 newtons per meter. That means that you get a force of 100 newtons for every meter that you stretch it, right? So we could ask, what would the size of the spring force be? We'll just do magnitude. If we stretch it by a displacement of, I don't know, 5 meters. Then we would just take the force of the spring is going to be equal to 100 newtons per meter. You multiply by 5, you get 500 newtons. This is just magnitude. The direction would depend on if you pull it to the right, the force is left. If you squeeze the spring, the force is going to be down. Again, the force always points towards equilibrium. Okay, anyone have any questions about that? What we'll do next is we're going to use this force to do this. We're gonna basically we're gonna basically just take this force, plug it in here for F, and then we're gonna be able to calculate in general what the work done by a spring is when we move between two positions. And later on, we're going to convert that into the potential energy stored in the spring. But we need to take a break, so we're going to take a break till 3:10 p.m. And when we come back, we'll do all that stuff.